In the first part of these reflections about the theory of relativity, I have been dedicated to prove the falseness of the principle that says that no object can be observed while it is moving at a speed higher than the speed of light. The other principle which gives its name to this theory is the principle of relativity. Einstein enunciated this, saying that the laws of nature have the same expression in all inertial referential ones. These referentials are the ones that are moving in a straight line and at a constant speed. This definition has a problem. The inertial referential does not exist in our reality. We are located on a planet that rotates on itself a full cycle every 24 hours and around the sun every 365 days, so it is impossible we can observe an inertial referential. Einstein said it was a very convenient invention, but at the same time, the formulas obtained for these referentials were found in others that were not subject to their limitations. And for example, in the Fizeau experiment, the values obtained by relativity were more related to reality than those obtained by classical mechanics. This made him assume that the relativistic formulas remained valid beyond the limitations imposed by these referentials, suggesting that it was possible to generalize, and thus proposed in a first attempt to operate on constant acceleration referentials. But soon another problem appeared. Every referential that moves with constant acceleration and enough time exceed any speed, however big, that is, the light inclusive, what forces theory to limit its action to a certain time interval, which is against the attempt of generalization. And in this situation, the idea considered by Einstein as the brightest of his life arises is that since gravitation subjects all bodies located in a certain environment at a constant acceleration, two phenomena will be matched, gravitation and the referentials uniformly accelerated. This part also presents some problems because the acceleration is, by definition, an action that changes the speed of the object to which it is applied, and the reality is that when we are sitting in our home under the gravity effects, this does not change, never change our repose. Anyway, Einstein avoids these difficulties by establishing a principle that defines the equivalence of inertial and gravitational mass. From here, he realizes that the generalization of the theory of relativity is a consequence of the generalization of the gravitation. In this respect, he realizes that the Newton formula indicates that the acceleration of gravity is inversely proportional to the square of the distance. That later in mathematics, he formulates the definition of curvature, and if this acceleration is multiplied by the mass of the body, the curvature increases, from which follows that the gravitational attraction of the mass curves space, even the path of light rays. From this observation, he developed his theory about the universe. As for the referential systems, leads his intention to generalize these to design a curved axis system as general possible, so that if, in these conditions, an elect physical law undergoes a coordinate transformation and the result is a covariate transformation, I mean, something that does not change its sign, structure, similar to what we said about what happens in the inertial referentials, then there is a law of nature. Well, at this point, I have to be noted that these transformations of coordinates are not possible because, as I warned in part 1, if I have a referential in which a star A is located 1 million light years, that means it passed that path a million light years ago, and another reference star is observed at 200 million light years, it is clear that occupies a different place than his path. Moreover, the coordinate transformation is to calculate the coordinates of a point A in one of the reference systems according to the coordinates of the same point in the other system, and it is impossible to perform this transformation because the star A occupies different points in each referential, and as I said in the first part, the observable universes lack common points. This same principle should apply to the Lorentz transformation and all those in which time appears as another variable in the reference system, and it is known that relativity always operates with 4 spacetime dimensions. Once the preceding remarks about gravitation were made, we will study their influence on the development of our universe. At first glance, we see that almost all celestial objects are gyros, with a polar axis around which spin and describe closed trajectories. Consequently, we will calculate the trajectory of the simplest gyroscope, that of a spinning top which we spin through the rope that we wind around it while it endowed a movement of translation in our impulse to launch. When we reach in the ground the stars to turn, we assume that the polar axis remains vertical and the top immediately begins to describe a circular path. This means that it is generating a centrifugal force, and we immediately assume that there is an attractor in the center of the path that balances the centrifugal force. But we look at the center and, surprised, we see there exists no attractor or anything that generates a gravitational pull. The motion of the gyroscope balances the centrifugal force, and we should be surprised that the gyroscope is one of the most studied objects in physics and mathematics, and we don't know their ability to balance the centrifugal force. We will therefore to calculate the trajectory of the center of the equator, I mean the maximum circumference, the spinning top. Well, we assume as before that the polar axis is located vertically so that the plane of the equator is parallel to the ground. Well, we see plotted in the figure the equator of the spinning top, and in the center of that circle the uppercase or translational speed of that spinning top. At the ends of the diameter AB also acts velocity v lowercase of points A and B in opposite direction. As a result of rotation of the spinning top, velocity b uppercase is equal to the length of a full turn of the path divided by time, and the v lowercase is the quotient of the perimeter of the equator divided by the time it takes a point of it to cross. ACP and COD triangles that forms the speed and radiuses of the equator, of the spinning top, and of the trajectory are similar. And also, if we equal the time it takes to make a complete rotation, the trajectory and the spinning top around itself, T uppercase is equal to T lowercase, it will result that the quotient of both velocities is equal to the radiuses of the trajectory and of the equator of the spinning top. In the case of the Moon, the time it takes to traverse its trajectory once is equal to the time required to rotate on itself once, so we can apply the formula obtained. On the other hand, both the speed and the radius of the Moon are known, so that by applying these values to this formula, we will have the radius OC of the trajectory due to the exclusive action of the translational motion of a gyroscope like the Moon. The result is 384,840 kilometers. The McDonald Observatory conducted a laser measurement of the distance between the surfaces of the Earth and Moon. It was corrected with the addition of the terrestrial lunar radiuses, and it turned out that between the center of the Earth and the Moon, the total distance is 384,400 kilometers. I mean a distance equal to that calculated for the lunar gyroscope. Considering the margin of error of the measurements of the velocities and considering that the distance Earth-Moon has slight variations, among other reasons because of its nutation. In short, there is no room for gravity to act an net effect to that obtained by the simple action of the gyroscope. Repeat this calculation for the Earth, around the Sun and all the planets of which we have data. The result is always the same: no room for gravity. There's no room for gravity as Newton understood it, which means that if there is no such gravity, theory of relativity of Einstein is dragged to a precipice. The issue is serious enough to act with the utmost prudence, forcing us to review the demonstration of Newton from his formula of gravitational force of attraction. In the 17th century, Descartes had published the text called Princess. Newton disagreed with what is said there, wrote a work titled De Gravitatione, which uses popular terms at that time, mentioning, for example, the planets had motor spirits that ran them floating in whirlwinds of subtle matter, or the concept of impetus and conatus by Jean Buridan, and even mythological stories, who was very fond. This text was not published in life of Newton, and after he died he appeared with a handwritten note saying not to be published, desired that was consistent with his later works. 15 years later, the Royal Society had already been established, and one of its founders, Robert Hooke, proposed the formula to measure the attraction of the planets according to the inverse square of the distance. His attempts to prove the veracity of this formula did not convince his colleagues of the Society, and one of them, Edmund Halley, who discovered the comet that bears his name, went to visit the home of Newton and asked what would be the path followed by a planet. It was submitted from a fixed point occupied by the Sun to the attraction proposed by Hooke. Newton replied that an ellipse. Halley asked if it was proven, and Newton confirmed yes, and he tried to search through his papers to show it to Halley, but he could not find. So told him that he would remake it, and within days it would send it to London. It took 6 months to fulfill his promise and send him what was the demonstration that if the planet ran an ellipse, it was attracted from a fixed point according to the formula of the inverse square of the distance. Well, months later he sent him the demonstration what Halley had asked in their interview, and is that if the planet is attracted by that formula from the Sun, its trajectory is an ellipse. He included this demonstration as problems 3 and 4 in a pamphlet of 12 pages that titled De Motu. During the following years, he never ceased to expand it and reached over 500 pages, with the known title Philosophiae Naturalis Principia Mathematicae, which is his major work. The proofs of Newton are very complicated and based on 2 points. First, centripetal force is equal to the gravitational force. Serious mistake because the centripetal force is perpendicular to the tangent at all times, while the gravitational force joins the point of its position and the focus of the ellipse. Both have different directions, so that they can never be equal, except at the vertices of the ellipse, where the tangent is perpendicular to the radiuses of the ellipse. On the second point, he applied to the above formula, which equals the centripetal force with force of gravity, the Kepler's third law, which says that the distance of the planet to the Sun cubed is proportional to the time takes to travel the trajectory squared. This position has no mathematical foundation. Moreover, a relationship of space with time always involves a movement. Well, there is no movement with that hypothesis, so its application is illegitimate. In this disqualification of Newton's demonstration, I have the invaluable support of Einstein, who considered the formula as an occurrence that was successful. He was always attentive to the epistemological aspect of his theory, which incidentally he modified several times. Since he read Kant's inaugural dissertation of 1770, he established that the importance of a theory is the mathematical formulation, because it depends only on the reason, and could thus prove its theorems without recourse to sensory experience. So the formula represented pure reality, while senses showed a reality deteriorated by interactions with matter, friction. He even said that the sensory reality was a naive reality. He always maintained this principle, while admitting the necessary collaboration of the senses. I think the last time he explained his thinking on this issue was in the letter addressed to Maurice Salaving 2 years before his death. In that letter, he states that to complete the formulation of a theory, it is precise a first phase of accumulation of sensory experiences of the phenomenon being formulated, then a logical examination of them, regardless of their origin. Because there is not a continuous path of reason from sensory experiences to the formulation of the theory. In this breaking point, he believed that it was necessary that the author invents the formula, or in other words, the theory. And here he gives the example of Newton, who accumulated experiences of how bodies wait on Earth. And as a logical development, he thinks the planets wait on the Sun. But it was necessary that apart from these previous steps, he invented the formula that regulates the attraction. And Einstein adds that among other possibilities, Newton proposed the formula of an attraction proportional to the inverse square of the distance. It means he does not consider the demonstration of Newton as such, but he was right about an occurrence which proved successful. Finally, I will refer to a project by Reinhard Genzel at the center of the Milky Way, where he found a group of stars of great magnitude revolving around a central point. This made him think that there was a great attractor that held those stars revolving around it. To his surprise, he found no attractor, as in the case of the top spinning around the center of its trajectory without any attractor. Therefore, within the current official paradigm, he had no other solution to propose that there was a black hole, which, generally speaking, has been accepted by the community of astrophysicists